notice how this triangle draws the eye to its slanted edge. If you are asked to calculate its area, the immediate temptation is to grab the numbers right in front of you, to multiply the bottom base of 5 by that visible slanted side of 4.9. Doing that produces a structurally flawed answer. The formula for the area of a triangle requires specific partners, not just any two connected sides. Most of us memorized the actual equation in school. Area equals 1/2 base times height. But reciting the formula leaves two major questions unanswered. Why is there a fraction of 1/2, and what truly defines a shape's height? To answer that, we have to strip the concept of area down to its absolute simplest definition. Area answers a single question. What is the total count of 1 by 1 unit squares required to cover a flat region, with 0 gaps and 0 overlaps? Counting these squares works for rectangles, because their right angles align with the grid. But drop a triangle onto that same grid, and its diagonal edges slice through the squares, creating irregular, incalculable fractions that are impossible to count by hand. Solving a triangle's area requires us to move past manual counting and adopt a new perceptual tool, the rectangle lens. Here is a standard right triangle, built on a horizontal base and vertical height. We reveal the hidden bounding box. The diagonal pairs every point with its opposite. Two congruent copies form a rectangle, so the triangle holds half the area. But look at this acute triangle. Its bounding rectangle isn't obvious. We solve this by dropping a perpendicular line to the base, creating two right triangles. We draw bounding rectangles around each. The original acute triangle accounts for exactly half of that total outer area. We rely on the rule of perpendicularity. A chosen base and its corresponding height must meet at exactly 90 degrees. Height is a strict distance from the opposite vertex to the baseline and can exist entirely outside the physical sides. This brings us back to the obtuse triangle, where the top vertex overhangs the base. By extending the baseline outward, we map a rectangle encompassing the entire structure. To isolate our triangle, we take half this massive rectangle and subtract the empty half. Applying these rules of perpendicularity and subtraction ensures that even the most warped shape ultimately reduces to the exact same geometric footprint. We communicate this logic through a universal proof. Take any triangle, duplicate it, flip it, and lock the shapes to form a parallelogram. Slicing the overhanging corner and shifting it reconstructs a rectangle with the exact same base and height. This logic holds under extreme conditions. Here is a fixed base sitting between two parallel lines. As the top vertex travels laterally, the triangle warps into extreme dimensions, looking completely different. Yet the height and base remain constant, dictated by the unchanged hidden rectangle. We have just moved through the 4 pillars of mathematical literacy: noticing the visual trap, reasoning through the rectangle lens, representing the perpendicular height, and communicating the proof. A geometric diagram functions as a rigorous component of the mathematical argument. The grids, bases, and right angle markers are the evidence proving the area. Perceiving these structural spatial relationships transforms geometry from a list of rules into a decipherable language. When you see the hidden rectangle, the formula is no longer a mystery.